Good day. The second part of study unit 6 focus on the last part of chapter 14. So we are going to look at sections 14.4 up to 14.6 in your textbook. Look at the outcomes in the study guide. You should be able to perform a hypothesis test to test if the regression model as a whole is significant. You should also be able to perform a hypothesis test to test if the individual regression coefficients are statistically significant. Then you should be able to determine the impact of each independent variable on your coefficient of determination. And lastly, you should be able to determine if the assumptions of the regression analysis are met or not. First of all, we are going to perform a hypothesis test to determine if the regression as a whole is statistically significant at a 1% or a 5% significance level. And we are going to use the F-critical values in our F table to determine whether we can reject the null hypothesis or not. So we also call this the F test, and we follow the critical value approach in making our decision and not the p-value approach. Then in step 1, we formulate our null and alternative hypothesis. So in the null hypothesis, you state that your regression coefficients are equal to 0. Remember, we use the sample data to test the population parameter. So here you write betas and not the estimated values given by b's. So practically in the null hypothesis, we basically state that none of our independent variables are linearly related to our dependent variable. Then in the alternative hypothesis, we state that at least one of our regression coefficients is not equal to 0. So at least one of our independent variables will be linearly related to our dependent variable. Then in step 2, we specify the test statistic and give the distribution of the test statistic. So our formula for our F statistic is given by this, where N represents your sample size, K is your number of independent variables, and R squared is your coefficient of determination that we looked at in part 1. And then F follows a F distribution with V1 and V2 degrees of freedom. So V1 gives us the column of our critical value in our F table, and that value is equal to our number of independent variables. And then V2 gives us the value of our row in our F table, and the value of V2 will be the number of values in our sample minus the number of independent variables minus 1. In step 3, we substitute our sample data to calculate our test statistic. And then in step 4, we read off our F critical values from our F table. So you read it off at V1 and V2 degrees of freedom at a specific significance level. Now, if I ask you to test the hypothesis at a 1% significance level, you will use the 0.01 F table in Appendix C4 on page 413. But if I ask you to test it at a 5% significance level, then you will use the 0.05 F table in Appendix C4b on page 415. Then in step 5, we can compare our F test statistic against our F critical value to make our decision, and you should also be able to interpret your decision. So if our F statistic is larger than or equal to our F critical value, then we can reject our null hypothesis according to our decision rule. So we can make the conclusion that the regression is statistically significant. Because there will be a linear relationship then between our y and at least one of our x variables. And then if our F statistic is less than our F critical value, we do not reject our null hypothesis according to our decision rule. So then we can make the conclusion that the regression is not statistically significant. So practically that would mean that our independent variables are not linearly related to our y. Okay, let's just recap on the chapter example. Our dependent variable was sales and we had two independent variables, radio and TV ads and then newspaper ads, and then our number of observations was 22, and we can determine our coefficient of determination from our model fitting statistics. So step 1, we write down our null hypothesis, which will state that our regression coefficient is equal to 0, and in the alternative we state that at least one of the regression coefficients is not equal to 0. Step 2, you write down the formula for your test statistic, and we indicate that F follows a F distribution with 2 and 19 degrees of freedom. Since our number of independent variables was 2, so V1 will be 2 and V2 will be 22 minus 2 minus 1, which will give us 19. For step 3, we can then substitute our sample data to determine our F statistics. So F will be 121.897. Then in step 4, we can read off our F critical value from our 0.05 table, since our significance level is 5%. So that will give us an F critical value of 3.52 at V1 and V2 degrees of freedom. Then if you compare your F statistic to your critical value, your F will be greater than your F critical value. So we can reject our null hypothesis according to our decision rule, and that means that our regression is statistically significant. And that means that at least one of the independent variables is linearly related to sales. You can then complete exercise 2F part 1 for me, please, to practice this concept. We can do a hypothesis test to determine if the individual regression coefficients are statistically significant. So will a specific independent variable be helpful in predicting our dependent variable? So we need to do a hypothesis test for each of the independent variables separately. In step 1, we formulate the null and alternative hypothesis. So in the null hypothesis, we state that the regression coefficient is equal to 0, and this implies that there is no linear relationship between our x and our y. Then in the alternative hypothesis, we state that the regression coefficient is not equal to 0, and this implies that there is a linear relationship between our x variable and y. And we can do this hypothesis test for all the individual independent variables. Then in step 2, we specify our significance level. So if it is not given, we use the default value of 5%. Like in the exercises, it was not specified, but usually I will give that to you in a test or exam. Then in step 3, we compare that significance level to our p-value from our computer output, and we interpret our decision. So if our p-value is less than or equal to our significance level, we can reject our null hypothesis. So our conclusion will be that our independent variable is statistically significant. But if our p-value is greater than alpha, then we do not reject the null hypothesis, and that will imply that our x variable is not statistically significant. We can obtain our p-values from the regression coefficients part of our computer output, and we look at the last column. So this value that is next to x1 will be the p-value for testing the regression coefficient for x1, and this will be the p-value that we use in the hypothesis test for testing the regression coefficient of x2. So let's look at x1 first of all. In the null hypothesis, we will state that beta 1 is equal to 0, and in the alternative hypothesis that beta 1 is not equal to 0. Since beta 1 will be the regression coefficient of x1. Then let's say we test it at a 5% significance level, then alpha will be equal to 0.05 in step 2, and then you can see here that the p-value for x1 will be 0.001, so that will be my p-value. Then if you compare that to your significance level, you can see that p will be less than alpha, so we can reject the null hypothesis. So that means that x1, that was the radio and TV ads, is statistically significant. So that means that x1 will be helpful in predicting sales. If we perform the hypothesis test for x2, then we will state in our null hypothesis that beta 2 is equal to 0, and in the alternative that beta 2 is not equal to 0. We can test it at a 5% significance level again, so alpha will be 0.05. And from the output, we saw that the p-value for x2 will also be 0.001. So again, p will be less than alpha, so we reject the null hypothesis, and we can draw the conclusion that x2, which represented newspaper ads, will also be statistically significant. So newspaper advertisement will also be helpful in predicting the sales. You can then try exercise 2D at the end of chapter 14, please. Our coefficient of determination measures the overall fit of the regression model to the observed data. So each of the independent variables makes a contribution to our coefficient of determination. And in this section, we want to determine which independent variable contributes the most to our coefficient of determination. Or stated otherwise, which independent variable has the largest impact on our regression model. If you look at the contribution of the variables to R square in your computer output, you will see that they give you the value of your coefficient of determination. And then in this column, we find the value of the coefficient of determination if a specific independent variable was not included in the regression model. So originally, your coefficient of determination will be 0.9277. If x1 is not included in the multiple regression model, then your coefficient of determination would have been 0.3533. So in the next column then, we get the contribution that a specific independent variable makes to the coefficient of determination. So x1's contribution is 0.5745 and x2's contribution is 0.3021. So x1 will contribute the most to the coefficient of determination and x2 will contribute the least. Or another measure that you can use is f square in the last column, which is the ratio of a particular independent variable's contribution to the unexplained variation. And here you will also look at the highest value in that column. So x1 will have the highest ratio, so x1 contributes the most to the coefficient of determination. You can then complete exercise 2E at the end of chapter 14, please. In the last section, we look at the assumptions underlying regression analysis. It's important that we test whether the assumptions are met, because if they are not met, then we can't draw reliable inferences about the population from the sample data. So the predictions of the regression model might be wrong. So there's two assumptions, normality and homogeneity of variances. The normality assumption can be tested by means of the normal probability plot on the computer output. And if the points of the normal probability plot lies more or less in a straight line, then this assumption will be met. But if there are large deviations from a straight line, then this assumption will not be met. For the homogeneity or variance assumption, we test it by means of the residual plot on the output. The variances of the residuals must be the same for all the values of our independent variables, even if the independent variables value increase. So the residuals must not show any pattern where the residuals fan out or funnels in. So it must have a horizontal band appearance. So there should be no systematic or discernible pattern in your residuals. If you look at the normal probability plot of the residuals, for the chapter example, the normality assumption will not be met because there are large deviations from a straight line on your normal probability plot. And a possible reason can be that you had a small sample size, since we only had 22 observations. The homogeneity or variance assumption will be met as there is no systematic pattern in your residuals, so you have more or less horizontal band appearance around 0. You can then complete exercise 2F part 2 at the end of chapter 14, please.